moving on to, and it's a perfectly smooth horizontal floor. Resolve the force horizontally and write an equation of motion for the box. So really, just to write that one line here, we need to do this much work here. For part A, we don't need to look vertically yet, but we do need to look at this force, think of how much is pulling it, and you know with 30 degrees you can just say, okay, I've got an equilateral triangle there, can't you? You know how this triangle here, if that's 30 degrees, might as well say so. As long as that's 30 degrees, this triangle here, do you see that it's half of an equilateral? Do you see where the equilateral might be? It might be, for example, we could make it here, couldn't we? Do you see an equilateral now? Do you see how the triangle we're looking at here with 30 degrees and a right angle, then this one must be 60. So our equilateral triangle is here, is 60, here's 60 down here, and here's 60, double 30. Yeah? Look at the clock. How many equilateral triangles can you see in a circle divided into 12 equal divisions? Have you ever wondered? If you're in a lesson and you're watching the clock for whatever reason, try and see the equilateral triangles. This one here is between 2 o'clock, 4 o'clock, and the middle of the clock, you could think.
You know that in, what do you say?
Equilateral.
Equilateral triangle. All the angles are 60 degrees, so 30 plus 30,
yeah.
60.
Yeah. Yeah, we can see how a 30-60 triangle is half of an equilateral. And that's why it's good news when we come across 30 degrees or 60 degrees. We don't need sine or cos. So we're told that the magnitude of the force is 10 this time. So we can see if that's an equilateral triangle, this is just going to be half of one of the 3 equal sides here, isn't it? That distance there is just half of 10, so that's why this is 5. But for part A, we need to do Pythagoras with 10 and 5 to get 5 root 3. Explain why this is 5 root 3. What we're trying to do, we're trying to get this result down here by doing Pythagoras. Yes, because we knew that was half of one of those equal sides.
Yes, so this is 5 multiplied by 5 squared
25
so 100
minus, yeah.
75.
Yeah. Because 75 is 5 times 20. I mean 3 times 25. Yeah, good. Yeah. So square root that, and you've got the square root of 3 times the square root of 25 is 5 root 3. Do that kind of thing when you're doing this. You know, don't be a slave to sine and cosine and therefore your calculator. So now, the question. Work out the acceleration of the box. Quite a lot that they're doing in just that one line. They're setting up an equation of motion. Remember what that means? Ma is what's left of the helping force. Now what's the helping force? We just found out that it's 5 root 3. It's the portion of this force here which is directed horizontally. So 5 root 3 is how much of 10 is pointing horizontally. All right, so just think of the horizontal aspect. Well, what does F equals MA say? It means MA is what's left of whatever's helping when you've deducted whatever's not helping. But there's nothing to deduct today, is there? If there's no friction today, but it's a perfectly smooth surface. Therefore, the equation of motion is just that this force here is equal to MA. We've not got to do any subtracting to say, okay, MA has got to be equal to all of that minus whatever the friction was. And that's going to happen soon. But for this first example that they're giving, no. MA just is, you're hurtling along with a rate of change of MV, because MA is the rate of change of NV, isn't it? NV being what? What do I mean by NV? What mechanical quantity is NV? Anybody? V is velocity and M is mass. Multiply them together, you get NV, which is if you get hit by a vehicle, you're afraid of both of those things, aren't you? You're afraid of the velocity they hit you with, and you're afraid of the mass. And we multiply them together to encapsulate what it is that's scary about the vehicle, which is its, yes, momentum. Momentum is the English word outside of maths and physics in England. People know what you mean by momentum, and it's what we mean in maths and physics by momentum. That scary property of a body that's hitting you with both mass and velocity, multiplying both. Now, the rate of change of momentum is ma. So you can see it makes sense that the amount of force pushing on something is going to be the rate at which it gathers momentum. If you apply a force to something, you give it momentum. And if you apply a force continuously, then that's going to be equal to the amount to its, what you're benefiting it in momentum. If there's nothing to subtract, because there's no friction. So F here just equals ma there, and that's what they're doing in that first line. And we can just say, okay, therefore ma equals 8a equals this force here of 5 root 3. 8a equals 5 root 3. We can say that a equals what? Drama. Can you make a the subject of that equation there? 5 root 3 over 8, because you're dividing the left-hand side by 8 as well. And that's what they've done, I hope. They put their units in as well. I'll put them in at the end, maybe. If I was actually doing an exam, I'd maybe put the units in there to show winning. But don't let them interfere with your algebra, basically. But part B, we do need to look vertically. And now this time, we have got to make an equation of motion, which is just as complicated as previously. We've got to see what all the vertical forces are. Now, one of them is the weight of the object. I might have drawn a force diagram here to indicate, and they have done a force diagram there. So this weight of 8, why have I made it so enormously large? Because I've had to think about the fact of what's bigger than what. It's in equilibrium vertically, so I've had to figure to myself, what are the upward forces? You've got a reaction force of the surface pushing back up. We're talking about that normal reaction of the ground up again against whatever is pulling down against the ground, yeah? So we've got a reaction force there, pushing up. We've also got the vertical part of this pulling force of 10 newtons, because it's probably a pulling string, pulling in that direction, isn't it? I'm moving it now, so look at what I'm doing, yeah? I'm talking about the action of the pulling string. But then how much of that is pulling upwards? Well, we do the trigonometry, and we just look at the equilateral triangle, and we see that it's obviously half of 10. Or we could say 10 times sine 30. But by the way, of course, sine 30 is one of those easy ones that you should know by thinking of equilateral triangles. Now, think about it. Which way is going which? Let's line up all of the downward forces against the upward forces, and we'll see that the downward force has to be considerably larger than the other two, because it's got to completely balance out both of the other two. So you could draw this kind of diagram to make that crystal clear to yourself. But they haven't bothered. But you've got to do that amount of work to see what they're on about, how they get this line here. They're saying, do an equation of motion. This one was relatively simple, even though there was acceleration. The ma was just equal to the helpful forces. This one here is relatively simple in that there is no acceleration. which is why all of the downward forces equal all of the upward forces. So what's the equation of motion? You can see it's that 8g equals r plus 5. Well, you can see that just by looking at the magnitudes. We've got this weight is opposed by two forces. The reaction, before anybody pulled, what does the reaction have to be? The reaction has to be equal to the weight. But when somebody starts pulling upward, and part of their pulling effect is upwards, then there's less reaction by the ground upwards. So that's how they're doing that one, and that's why their equation of motion is that 8g equals r plus 5. So r equals 8g minus 5, which is what they get.